So we're going to look at the orders of magnitude on this one. And what are they telling us? Well, that 2 and the 5 aren't going to play a huge part, but they're going to play a little part. You're going to see in a second. What's going to really play a part is what varies with n. Constants, generally speaking, don't play a huge part in this, but they're going to play a little part. So the stuff that doesn't, if this wasn't there, that would be n squared divided by n to the 4th. Or that would be 1 over n squared. So this stuff right here is, man, again, my board is way out of sync. This is happening like every day now. I gotta recalibrate the board. Sorry. I don't like it when I'm writing and it's writing 6 inches away. That's not good. So this is going to vary. N squared divided by n is going to behave like 1. Like 1 divided by n squared. Okay? Those two are going to behave like that. The 2 and the 5, not much impact. But keep them in mind. So 1 over n squared converges or diverges? Pop quiz. It's a p-series. It blank as a p-series with p blank. It will converge.
What?
It will converge. Converges as a p-series with p greater than 1. This is p. So less than or equal to 1, it diverges. Greater than 1, it converges. And so I'm just doing that to throw some pitches at you and hopefully reinforce our tools, sharpen your tools a little bit. Right? It's springtime. All the tools in my garage need sharpening. Okay. So that converges. So I suspect this is going to converge. So we suspect our series, this series, let me just write it here. Converges. Okay. Now, we only have a couple of convergence tools available to us. One is the integral test, and we could integrate that. We know how to integrate that. It's ugly. Too much work. We're lazy. So we're going to use the direct comparison test. So to show this series converges using the direct comparison test, we need A, fill in the blank, larger or smaller. Series that converges or diverges. Fill in the blank. Do we need a larger series or a smaller series? And we're looking for one that converges or diverges.
A larger conversion.
Perfect.
Oh.
Perfect. Right? You need a larger that converges. Now, this part over here is the easy part. Because if we suspect it converges, whatever series we find has to do the same thing. If we suspected it diverged, we put diverges here. Okay? And it'd be a smaller series. That's that little 2x2 thing we made last time. That is going to become its own slide over the summer. Right? I'm going to be sitting at some Christian camp's dining hall, probably at 10:30 at night, looking at my slides from this year and incorporating changes. And that's going to be a change. I'm going to add that one. And plus, be sure to tell me if you have any idea that would help you make these slides more helpful for you. I've said it before. Mention it, right? I'm definitely open. Okay, so that's what we're looking for. Okay. Let's see. What series do we have that is larger that converges? Well, this one converges, right? That one converges, but is that one larger or smaller than that one? It's kind of hard to tell. Okay. That one converges. So we need something that is slightly bigger. So to make something bigger, I can make the denominator smaller, right? Make the denominator smaller. That makes the series bigger, right? Or I can make the numerator bigger. So numerator bigger or denominator smaller. So I'm looking at my series here. How could I make this slightly bigger? Get rid of that 5. That would be one way. If I get rid of the 5, I make it smaller since it's added, right? So that would make the denominator smaller. That would make the series bigger. Now note, this whole thing here equals AN. Note that n squared plus 2 over n squared plus 5, that's AN, that is going to be smaller than n squared plus 2 over n. I need an n to the 4th here. Got a typo right here. This is n to the 4th. And we're going to call this Bn. Okay. Now you got to show some kind of work like this on your paper. Otherwise, there's a 50-50 chance you're going to guess something that diverges or converges. This shows, this is clear that without that 5, that becomes bigger because the denominator is smaller. All right. Now, do we know whether this converges or not? That's another thing. It's one thing finding a bigger series, but it's got to be a bigger series that we know converges. Right? That we know converges. All right? So sigma n equals 0 to infinity of this series how do I show if that converges or diverges? Here's another ninja move. Put this one on your Swiss Army knife. Right? We haven't studied series exactly of that form. In fact, most of the series you're going to see are not going to be exactly of the form of the theorem. You just got to show that the theorem still applies. Well, this equals correct? Do some canceling. This would equal n squared divided by n to the 4th is 1 over n squared plus 2 divided by n to the 4th Now, you remember we had a theorem that said this is the sum of a sum. So the sum of the sum is the sum of the sums. What does that mean? This equals, we got a little bit of a problem. We have a little bit of a problem. We are going to have to ignore, you remember you can ignore finitely many terms? And at the beginning of a series, you can ignore finitely many. We're going to have to ignore the 0th term. And I know this is a pain, but I should have done this before. We're going to do this from 1. The reason why, for 0, that n to the 4th is undefined. So make this a 1 right here. 1 and 1. So this is going to be sum n equals 1 to infinity, 1 over n squared, plus 2 times the sum, 1 over n to the 4th, these two sums, these series, I keep saying sums. A series of a sum is the sum of the series. That's what I should have said. But these two series both are p series. Both converge as p series with p greater than 1. Over here, p is 4. Over here, p is 2. Both of those converge. And this is bigger than our series that we're considering. This is bigger, remember? We have to establish this first. This is key. You got to put that there and communicate that you know that. Right? So since our bigger series converges, this one converges by the direct comparison test. Ergo, sigma n squared plus 2 over n to the fourth, n equals 0 to infinity. Now I can't do 0. 1 to infinity. Converges. And our original one converges by the direct comparison test. Right. All right. What's the pattern? You've got to come up at the beginning with a hunch of whether you think that converges or diverges. And to do that, you look carefully at the orders of magnitude of the numerator and denominator. You see down here, you have n to the fourth, top is n squared. That means those two are going to behave about like 1 over n squared. Right? That made me suspect that it converges, because 1 over n squared converges as a p-series with p greater than 1. We're using this p-series thing a lot. Greater than 1 converges. So we suspect that our series in question converges. So now I need to find a slightly larger series that converges in order to use the direct comparison test. And so we came up with this guy right here. We came up with this guy here by dropping the 5 in the bottom. And then we showed that one converged because we broke it up into 2 p-series, both with p bigger than 1. Both those p-series down there, these right here, are p-series with p bigger than 1, so they both converge. Therefore, our original one converges. Questions? Complaints? Never mind. Ooh. This is interesting. Does that converge or diverge? So this one, you have to come up with the series. And that's just going to be, this is the nth term right here. You have the nth term sitting right there. Right? So this equals sigma n equal 1 to infinity, 1 over n 2 n minus 1. Now, to make this harder, suppose you weren't given that. You'd have to discern that pattern from this pattern. But you see in every case down here that you have numbers 1, 2, 3, 4, and the second number in the denominator is well, that's a 1, but this is 1 bigger than that, 2 times that. Or 1 smaller than 2 times that. This is 1 smaller than 2 times that. This is 1 smaller than 2 times that. And so that's 2n minus 1. So pick up that pattern. Question. Does it converge or diverge? What do we suspect? We suspect look at the orders of magnitude in the top and bottom here. The orders of magnitude. This bottom is going to be 2n squared minus n. Now, as n gets big, the top is going to stay 1. The bottom, this is going to be the boss here. This guy is going to run away from n. N squared is going to get much, much bigger, much faster than n. So that bottom is going to behave, this is going to behave sort of like n squared in the bottom.
So it's going to converge.
Converge. That's what I suspect. So this whole thing here is going to behave like 1 over n squared, which converges P series with P equal to, check that, 2, which is bigger than 1. The important part is not that it's 2. The important part is it's bigger than 1. So we suspect that it converges. So what do we do? Just like the last problem, we need to find a slightly larger series that converges. Now, just to note, so we don't forget this, notice all these are positive terms. They're always going to be positive. That's a condition for the direct comparison test. The same over here with this one. These are always going to be positive for large, Another thing too is it's okay if it's positive from some point on. Like suppose this were n squared minus 5. For low values of n, it would be negative, right? That's okay, as long as it's positive from some point on. Why? Because you can always ignore the first finitely many terms. Whether they're a positive number or a negative number, they're not going to affect the convergence. Because if something goes to infinity, plus or minus 100 ain't going to do nothing. So here, it's note that all these are positive. In order to apply direct comparison test. All right. All right. That's just a reminder. That's in all of these. Anytime you're applying the direct comparison test, don't forget, you got to have all your terms positive from some point on. All right, so we suspect it converges. We need a smaller, bigger series that converges. Need to find. Let's find. Larger. series that converges. Question. If AN is 1 over n 2n minus 1, I'll lower that. What would be a larger series that converges? Let me tell you what I'd be tempted to do, but I don't think it works. This last problem, what did we do? We knocked something out of the denominator, remember? We knocked a positive term out of the denominator, which made the denominator smaller. So this equals what would I like to knock out of the denominator? I would like to knock this thing out of the denominator. Don't put that on your paper. But doing that, I'm knocking a negative out of the denominator. That makes this smaller. Hold on a second. That makes the denominator, excuse me, bigger. The denominator bigger makes the ratio smaller. If I eliminate a positive term, that makes the denominator smaller. If I eliminate a negative, it makes the denominator bigger. So 1 over 2n squared, I know that converges, but the problem is it's smaller. 1 over 2n squared, I would like to compare it to 1 over 2n squared. But that won't do any good because 1 over 2n squared is smaller. Wah, wah, wah. Back to the drawing board. Back to the drawing board. How can, what's a good way to handle this? Let's see here. I need to make the denominator smaller, not bigger. Smaller. So another ninja move, turn this n into an n squared. So that will be, if I make it smaller, if this is n squared, I'll be subtracting something bigger. And so that makes the denominator smaller and the new series bigger. So this is less than 1 over 2n squared minus n squared. How does that help us? Okay. Well, 2n squared minus n squared, that's convenient. This equals 1 over n squared. Let this be our bn. You got to, these things take thought. I can remember, I still have to stare at some of these a long time. And in fact, when they get too sophisticated, they get really, really hard. And we have to use other theorems. What I want you to see is that if I would have knocked this n off, that would have made the denominator smaller. I'm sorry, bigger. If I'd knocked this negative n off, that would have made the denominator bigger. All right? So if I knock, and I'm going to erase what I'm about to do. If I would have knocked that denominator or that n off, that would have been this. But showing that converges, but it doesn't help us because it's showing that a smaller series converges. I need a bigger series. All right. So now, sigma, I'm going to do here sigma bn. You don't have to do that, just for clarity. This converges as how many times am I going to say this? As a p series with right. Teacher sleeping in class again. What does that mean? So converges by the direct comparison test. Now it's that special time of class where I am going to save this, get out of it so I don't lose my work. What slide am I on? 58. 58. I'm going to send that to Joel. Yeah, the Wi-Fi's been going. It's been fritzing out in SAC. The Wi-Fi. It worked yesterday morning. It didn't work all day Friday in SAC. The YC South network didn't work all day Friday, and then I sent in a help desk ticket. Joel suggested some things, and then they didn't work. And he came over here, and I just handed him my phone. I said, "Look, you here. There's the evidence." And he couldn't get it on Wi-Fi. So yesterday it worked in the morning and not in the afternoon. But the Wi-Fi that was connected to the wall worked. I'm sorry, the internet when it was connected to the wall, not on Wi-Fi, worked. It's the Wi-Fi that didn't work. But now it looks like there's some problems with the connectivity. All right. Limit comparison test. This is a brand new test. Brand new test. All right. And I need to. I need to add some homework here. That's for me. When I do that, I'll send it to you. All right, limit comparison tests. Okay. All right. This is the one that we just did down here. This is the problem, this is the problem. Encore solution. You're going to like limit comparison tests because it's back to limits, which now you know limits inside and out, right? And you don't have to come up, is that bigger or smaller? And do I need a bigger series that converge that? You don't have to think through that, okay, for the limit comparison test. But the limit comparison test doesn't work sometimes that the direct comparison test does. So the limit comparison test says I got to have two positive series again, right? And that if the limit of one divided by the other equals some number that is finite, it's not enough that this limit exists. It has to equal something that's finite. It cannot equal infinity. And it has to be positive. Okay? Then both series, the one on the top, the series of AN and series of BN, they sink or swim together. They either both converge or both diverge. Both converge or both diverge. All right? So you remember what we've been doing here? When we form our suspicion, we look at the orders of magnitude here. Right? And we saw that this is kind of 1 over n squared. Right? Kind of. Now we can use that 1 over n squared directly. Because here it's hard to compare, is this 1 over n squared bigger or smaller than this? Well, it turned out to be bigger. Just look over here. The 1 over n squared turned out to be bigger. But we didn't know that coming in here. So you still start your solution the same, coming up with a suspicion. Right? But with that suspicion now, we're going to find something of the same order of magnitude and put one series over the other. And if that limit is finite and positive, then both series converge or diverge. Now, you want to compare it to a series that you know. If you don't know if this one converges or diverges, it doesn't do any good to compare it with another one that you don't know. You got to compare it with another one that you know. And then if the limit is positive and finite, then the one you know and the one you don't know got to do the same thing. So back down here, right? This right here is, remember, that's AN. From our last example, we kind of saw that this behaves like 1 over n squared. So we're going to let now we don't care if 1 over n squared is bigger or smaller than the stuff over here. Now, using the direct comparison test, we did care. For the limit comparison test, we don't care. All right? And so you're going to put one over the other. Right? So now we're going to do limit. N goes to infinity. AN over BN. Right? By the way, you can put BN over AN too. You can flip these. Doesn't matter. That's going to be, here comes some algebra. N goes to infinity. What is AN? AN is the numerator. 1 over n to n minus 1. The denominator, 1 over n squared. Invert and multiply. Invert and multiply. Invert the bottom, multiply by the top. Okay. That's going to equal limit. N goes to infinity. The top is n squared. The bottom is 2n squared minus n. Right, that denominator is 2n squared minus n. How do you evaluate that limit? What's our, we've learned at least 2 ways of evaluating that limit right now. It's infinity over infinity. That's a hint. Easiest way is L'Hopital's. So this right here is infinity so we're going to apply L'Hopital's. Okay. That's still infinity over infinity. Apply L'Hopital's again. The top 2, the bottom 4, that's going to equal 1/2, which is positive and finite. Oh, by the way, L limit comparison test, LCT. Ergo, our original series converges by the limit comparison test. Oh, one more thing. I left off something very important that I'm going to want you to include. But I'll let you copy that right down. Okay. The important part is we let Bn equal something. We got to say what this does. Does that converge or diverge? We have to say it. So this converges as a p-series with p greater than 1. So you got to say what it does and why. And why. Now keep in mind that right now we've been using this p-series thing to death. But we're gaining more and more convergence theorems. Right? We have the direct comparison test. We have this limit comparison test, there's going to be more. A lot more, actually. Yeah. Yay. That's all chapter 9 is. Chapter 9, a bunch of convergence theorems for limits. All right, so we picked one that had the same order of magnitude. That has the same order of magnitude as the one in the question. We put one over the other, and this would have worked just the same if we flipped. If we'd have flipped this, our limit here would have been 2. It would have been 4 over 2 here. You'd have gotten 2. That's positive and finite. It would have worked. So it doesn't matter which one you put over which one, as long as you compare it to another one whose convergence you know. If you compare it to another unknown, it doesn't help you. So we knew the convergence of this one, so that helps us. Yeah. I look at my notes once in a while. Yes. Yes. Now we did this one. Right? This is a retro, and I might even call this one a encore solution to this. Encore, that's what we call it. Okay. What do you compare it to? What do you compare it to? Well, how did we do this the first time? Remember? We compared it to sigma 1 over 3 to the n. In other words, we dropped the n. What did we suspect happens here? We suspected, by the way, you don't need to suspect anything for the limit comparison test. But this one we suspected converged because it's got a 1 on the top and all this stuff on the bottom is just going to get bigger and bigger and bigger. This is going to get bigger really fast. Okay. So we expected that to get small very fast. So the bottom was a much higher order of magnitude than the top. So we suspected that converged. And so we compared it to, don't write this down, we compared it to sigma 1 over 3 to the n. And since we made the denominator smaller, we suspect this converged, we made the denominator smaller, that is a bigger series that converges. And that's how we did it. Okay? Now, let's do it a different way. But the same line of thinking. Call this AN. And we're going to compare to BN is 1 over 3 to the n. Note, sigma 1 over 3 to the n converges. Why does it converge? Geometric series this time, not p-series. As a geometric series with absolute value of r is 1/3 is less than 1. Right? That was the criteria for convergence. Okay, so now we're going to do the limit comparison test. So over here, apply. Actually, let me do something else. Apply. And I'm going to put that same thing over here. Down here, multiply. So how does that work? It doesn't matter which one you bring on top of the other one. So this is going to be limit n goes to infinity. Right. Let's put b in the numerator just to be rebellious. 1 over 3 to the n. Denominator 1 divided by n plus n. By the way, when we did this, we did this last time over here. This first limit, as n goes to infinity, this is a 0 over 0 case right here. We could have applied L'Hopital's right there, because it's a 0 over 0 case. The only problem is, those both, the numerator and denominator, if you take the derivatives of them the way they are, they're going to get really messy. So we simplify some, then take the derivatives of top and bottom. That's what we're going to do here. This top goes to 0, the bottom goes to 0, so this is a 0 over 0 case. We could apply L'Hopital's rule right now. It's just that we're lazy. So we're going to simplify some, right? So this equals limit n goes to infinity, invert and multiply. So you're going to have 1 over 3 to the n, that's the numerator. Denominator, 3 to the n plus n, 1. Okay. This is limit n goes to infinity. And that's an infinity over infinity case. So 0 over 0 cases can usually be made into infinity over infinity cases, right? So this is an infinity. So we're going to apply L'Hopital's. And we got to have at least one pop quiz. We got to have at least one today. You'd feel neglected. Ready? Limit. What's the derivative of the top and what's the derivative of the bottom?
Your wildest cravings will come true with the $5 Chalupa Cravings Box.
They got to show something from Taco Bell, right before lunch. This is a chapter 5 derivative problem. That's why I'm picking it. Okay. Good news is, I hope that refreshed your, well, I hope you got it right. I hope you got the derivative of that right. But if you didn't, this hope refreshes you on what the derivative of an exponential function is. Okay. Number one. Number two, got bad news. This is still infinity over infinity. Those do not cancel. You can't cancel that. You do that, a kitten dies. Its tail is very sad. So, L'Hopital's again. Limit. The derivative of that again, derivative of the 1 is 0. This is going to be log 3, keep in mind, is just a constant. So that's going to be log 3 squared, 3 to the n, divided by log 3 squared, 3 to the n. Now those you can cancel. Equals 1. Well, student will observe. This is positive and finite. Ergo. Our series converges by the limit comparison. Right. Now, this time I didn't forget that little part I told you up at the top. We compared it to another series that converges. Okay. We compared it to another series that we knew to convert that converged. Anytime you do the limit comparison test, whatever you compare it to, you got to compare it to something whose convergence you know, one way or the other. Even if it diverges, I got to know it diverges. All right, so we didn't have to stop and think whether 1 over 3 to the n was bigger or smaller than this. So that's an advantage over the direct comparison test. You don't have to stop and think, okay, I think it converges, so I need a bigger or a smaller series that converges to 0. You don't have to go through that in this problem, but you do need to know that for other problems. That's an advantage. That's an advantage. Here is some homework. Use the limit comparison test to determine whether this converges or diverges. And as a way to review for your pedagogic edification, verify your answer using the integral test or the direct comparison test. Right? So apply one of these to that to be sure your conclusion from what you get from theorem 9.13 is correct. So what you're going to do on this one, you're going to find another series whose convergence you know. And you're going to take the limit as n goes to infinity. Now, keep in mind that for the limit comparison test, if that limit is 0, doesn't work. The limit comparison test doesn't apply if the limit is 0. It's got to be positive, greater than 0, and finite, less than infinity. Right? So if our limit is infinity or 0, that doesn't tell us anything. Right? So this is a good homework problem. I know what you're thinking. You're going to have to work on your relationship. Alternating series. We just got a couple minutes. Alternating series, we've seen these already. So alternating series have a -1 to the n or -1 to the n plus 1, something like that in them. They alternate sign, positive, negative, positive, negative, positive, negative, positive, negative. They alternate sign. All right? Okay. These converge if the following two conditions are met. And you've got to know these conditions. Must. Number one. The nth term without the 1 over n, or the, excuse me, minus 1 to the n, the an part has to go to 0. Must. Because if it doesn't go to 0, if it goes to say 1, it's going to converge to plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, which doesn't converge. So the part without the minus 1 to the n part has to go to 0. Second, the part without the minus 1 part has to be, what was this word? What do they call it? Non-decreasing. Wait a minute. No, non-increasing. Sorry about that. Fake news, non-increasing. Right. And this says for all n, really, for all n greater than or equal to some big n, i.e. from some point on. Okay. Now, the student will call this right here. Let's look at these two. These are very familiar, and believe it or not, we have enough time to do it. This is the harmonic series. It diverges as a P series how in the world did that happen? I don't know how to, I don't even know how to do that. I would like to know how to do that as a P series with P equal 1. And P equal 1 is less than or equal to 1, right? So it diverges. What about this guy? If we put the minus 1 to the n in here, right? This is our an. Our an here is 1 over n. Right? Our an is everything except the minus 1 to the n part. Note, number 1, condition number 1, the limit as n goes to infinity of an is the limit as n goes to infinity of 1 over n equals 0. Check. We're checking the conditions for the alternating series test. Oh, by the way, AST. AST. Right? So we're check conditions for AST. 2, an is 1 over n. That is going to be larger than 1 over n plus 1, which is an plus 1. We had to show that an, that was the second one here. Right? An's got to be greater than or equal to an plus 1. That's the second condition. Check. Ergo. Sigma minus 1 to the n over n equals 1 to infinity converges by the ST. Wait a minute. But we started a couple minutes late. So I feel self-justified in my own eyes, right? Teachers always do that, right? Okay. Yeah. All right. We will leave it there. And hopefully we'll see. Jesus, hope you're all right, bro. See ya.